Great. Welcome everyone. 欢迎大家来到 Harvard CMSA seminar. Very happy to have Shu-Heng Shao from Stony Brook, and we have a very casual discussion today. So feel free to interact with Shu-Heng and ask questions.
Good.
So his title is Cluster State as a non-invertible SPT base. So let's welcome Shu-Heng. Please.
All right, thank you. Well, thank you for coming. Yeah, so I want to keep this. I don't even want to call it a talk. I think it's just we chat together about something we like to talk. So feel free to ask me questions. I think I want this to be more of a discussion. But on the other hand, this is going to be a rather technical talk. I've been working on this project for a long time. But most of the invitations I got recently are about some open style or general vision talk about this subject. I'm at the point I'm getting a little bit tired of those style of talks, so I want to talk about something technical today. But because of the technical nature of this talk, maybe might get easier to, but for people who are not working on this subject, might be you might get lost, but just let me know and I'll try to. Okay. And the talk is structured more like a condensed matter style. There will be very little. So this is work in progress with Saham Sapnashri, postdoc at IES. They're writing the paper. Hopefully the paper will be out soon. All right, let's get started. So what's the setup? The setup is a 1D system, or 1 plus 1D multiplexing. And we have string state. So the space is a one-dimensional circle. It will always be a circle. Actually, throughout the talk, I'll never cut it open. It's always closed and periodic. 1, 2, 3, all the way to L site. And on each side, there's a qubit. On each side, there's a two-dimensional qubit space. On each side, I have the Pauli operators, Xj and Vj, obeying the standard Pauli algebra. And for simplicity, let me assume L to be even. Now, there's something interesting to be said when L is odd, but let's start with L. In fact, later on, I might even need L to be a multiple of 4 or multiple of 8. So it gets even more interesting. But let's stick to the simplest case. All right. So this is the Hilbert space. For the total Hilbert space, this is the tensor product of all these little qubits. And we have a 2 to the L dimension space throughout. Great. Now, let's consider 2 Hamiltonians. First one is a trivial paramagnet, where the Hamiltonian is just a sum of X terms. And the second one is the plus value. And I always periodically identify my index J. So here, so far, I'm just reviewing the standard cluster Hamiltonian. So these are 2 Hamiltonians. They look different, but if you look at the spectrum, they're actually very closely related. So if you take the trivial Hamiltonian, the ground state is just a product state. So in my convention, X acting on plus or plus or minus is plus. So plus and minus are the eigenstate of X, and 0 and 1 are the eigenstate of Z. So for the trivial Hamiltonian, this is the ground state. The spectrum looks like this. Energy, which is a unique ground state. And then there's an older one gap. because any excited state will flip the sign of one of these terms and give you an order one gap. So it's really a trivial Hamiltonian. You have a unique ground state and a gap. But this Hamiltonian, even it looks slightly different from the previous one, but there's again a unique ground state, the cluster state, which I'll show you a little bit more in just a minute. And there's an order one gap. By order one, I mean as I take L to be larger and larger, it doesn't skip. Now, why is this so? Well, there are several ways to see it. Take this Hamiltonian. We have L terms in the Hamiltonian. Each term is a product of Pauli operators. And one of the defined, so each term is an element of the Pauli group. Now, one of the defined property of the elements in the Pauli group is that its trace is zero and its eigenvalues are always +1 and -1. So these are commuting projectors. Each projector is a Pauli operator, and therefore, if you have L of them, the space where you diagonalize all of them, one dimension. So in the technical term, this is a stabilizer. And in fact, the two states, the two Hamiltonians are related by a unitary transformation. It's cluster state. Be written the product 1 to L times the CD gate. Let me just write the definition for the CD gate here. J1, J2 is a half 1 plus 3J1 plus 3J2 minus 3J1. CZ is a local unitary operator. This whole thing is a unitary operator. It's very easy to check that if you conjugate a trivial Hamiltonian by this unitary operator, let's call this B maybe. If you conjugate the trivial Hamiltonian by B, you get a cluster Hamiltonian. So the two Hamiltonians are unitarily equivalent. In fact, it's stronger than that. This unitary is a finite depth circuit, meaning that you can write it as two layers of product of non-overlapping local vectors. So you split these terms into J even and J odd. These are two layers. Each layer is a product of non-overlapping local vectors. So this also explains why the spectrum of these two is the same. So far I just talked about two totally trivial Hamiltonians. And if you look at each one of them individually, it is pretty much featureless. Now, the interesting thing is that their relative difference is meaningful. That's what I'm getting at. Hopefully, so far everything is here. As I was saying, D is a finite depth. And this implies that product state, the cluster state, and the same things. If we do not impose any global symmetry. So next, we are going to impose the global symmetry. And at that point, these two Hamiltonians will represent two different phases. The global symmetry that will be of interest to us is a Z2 cross Z2 symmetry. The superscript E and O means that they're generated by the following two operators. One of them is the product of xj but only on the even side. The other is the product of Rj, but only on the odd side. So clearly eta even and eta odd form a Z2 cross Z2 symmetry, and you can check that these two Hamiltonians are both invariant under these two symmetries. Now, if you impose these symmetries, what you realize is that the gate, namely CZ JH plus 1 of our finite depth local unitary D, is not Z2 cross Z2 even. It's not Z2 cross Z2 symmetric. Well, I should say that D by itself is Z2 cross Z2 symmetric, but the individual gate is not. And this implies that, and I think one can furthermore show that there does not exist a finite depth local unitary with a Z2 cross Z2 symmetric gate to relate the cluster state to the product state. And that implies that the cluster, the product state, the cluster state are distinct D2 cross D2 SPT. So SPT stands for symmetry protected topological. In fact, the space of a symmetry protected topological basis in 1 plus 1D is classified by H2. More precisely, it's a tensor over H2. And if G is Z2 plus Z2, this is just Z2. So there are two distinct SPD bases for Z2 plus Z2, and cluster and the product states are these two states. Now, in the literature, people commonly declare that the product state is the trivial SPD and the clustered state is the non-trivial SPD. That is a declaration. It is not an invariant statement to make. The invariant thing to say is that their difference is non-trivial. Generally, it's meaningless to say which one is more trivial than the other. And this point will be more clear as we go to the non-invariant.
Yes. If you cut open the chain, can then you then
I'm getting into that. In fact, even if you cut open, actually, I'm not going to cut open the chain, and the reason will be clear when we go to the non-invariant case. But I will do something very closely related to cutting open. Sorry, just 1 second. I'll get to something very closely related to cutting open. But let me just say the following. People usually say that if you take the cluster state, a cluster Hamiltonian, you cut it open. And if you also want to preserve the Z2 cross Z2 symmetry, then there has to be boundary degeneracy. But there's an ambiguity in what we mean by preserving the symmetry on the image. So one way I can think about how to define it is that you want the symmetry, you want the system you want the Hamiltonian on an open chain to commute with some Z2 cross Z2 conserved operator. That's criterion number 1. Criterion number 2, you want the Z2 cross Z2 operators to look on the open chain, to look locally identical to the one on the closed chain. Namely, locally, they have to be a product of this. Now, if you only demand these two conditions, in fact, for the cluster Hamiltonian, you can actually write down a boundary condition such that there's no boundary degeneracy. And the trick is that you don't view the eta as a product of X. You view it as a product of ZXZ. On the closed chain, you couldn't tell the difference because the Z O pair annihilates. But on an open chain, you could. So that's actually one argument that there's really no distinction. There's no sense that the cluster state is more non-trivial than the product state. It's really the relative thing that matters. And in fact, later on, I will give a presentation that will never force us to talk about things on the open chain, which will be more convenient for me when I get to the numbers. Yeah, sorry.
So if neither one is more topological than the other, is there like a higher symmetry critical point that has, in which you could like break a symmetry and then have the symmetry vector of one exchange the two phases?
So you can interpolate from one phase to another, but then there will be a, say, for some of the interpolation, there can be a gapless.
Yeah, because you know what the exact symmetry is of that distorted that gapless point that permeates the two phases?
Let's see. I think it has to be probably some Z2Q, right? There's probably just one. That's right. Yeah, I think that's right. You just have one additional Z2. So now you have two Z2s, but at the transition point, you will have a third Z2, and the three Z2 have some kind of anomaly. In fact, that anomaly will show up later on.
Do you think it's
Yeah.
three part of a 3Z2 or will it be even non-abelian group?
No, it's the group is Z2Q, which is a bit. But anyways, I'm not going to talk about the transition. It's a CZX product, but I'm not.
When I look at the upper two classification, then it's a group, right? There's an triple identity element, there's a non-triple element.
Good. So GSPT is not classified by H2. It's a tensor over H2. And that's one thing that people don't emphasize enough in the literature. But it's really a tensor. There's none of them. Neither of the two is more trivial than the other.
So is there like a stacking group that I can stack the field guy and sort of make that like the group structure of understand?
Yeah, but then you have to declare which state you take to be the resource. So when you do the stacking, you always assume there's some free resource you can take. That's a declaration. And this point will become even clearer when we go to the non-invertible case. Okay, good. So where was I? Okay, so these are two distinct SPTs, and the statement that these are two distinct SPTs means that if you start with one Hamiltonian and you want to adiabatically deform your Hamiltonian to the other one while preserving the symmetry, there has to be a phase transition. By the way, another nice analogy of the fact that these two SPTs are on the same footing, it's actually, I think it's clear from the continuum point of view. The prototypical example of a SPT in the continuum is to take a biofermion, 3+1, a free biofermion. Now, a free biofermion can have a complex mass. Now, if you impose a time reversal symmetry, then the mass has to be real. Now, you can turn on a positive mass versus a negative mass. Both phases individually look completely trivial. You have one unique ground state and then the older one gap. So just like these two cases. But there's really no sense that the positive mass biofermion is more trivial than the negative mass. And indeed, the two phases you can be continuously interpolated if you give up on the time reversals. On the lattice, it's very tempting to say that the product state is more trivial just because we choose a particular microscopic realization of the system where we have a tensor products, the Hilbert space, etc. But more invariantly, this distinction doesn't exist. I'm not saying that it's wrong to call the product state trivial. It's a declaration. It's a choice to be made. If you make that choice, I cannot complain. That's the nature of the tensor. You can pick any one of the elements to be the identity element and continue with your life. There's nothing wrong about it, but it might get confusing when you get to more general. All right, good.
So the statement you make about the 3+1 biofermion, it's complex mass. I would like to go to the example, but let me just finish that. So that statement for like a DEM3 will be omega 4 of the pin classes.
That's right.
This is in.
That's right.
But if you remove time reversal,
That's right.
which will be spin. So both omega 4 spin and omega 5 spin things both are 0.
But we're just
Yeah,
looking at omega 4.
Yeah. There's no cost. So what's the analogy here? if I want to phrase to that language.
It's a Z2 cross Z2. What the analog of the time reversal here is the Z2 cross Z2.
Right.
The classification is H2 rather.
But do you want to remove some symmetry? You remove Z2 with
If
Z2.
you remove the Z2 cross Z2, you can continuously interpolate the two. If you impose the Z2 cross Z2, you cannot.
Any of the Z2.
Yes.
Yeah.
If you remove,
Any of one.
if you give up on one of the two Z2s,
Yes.
then the two faces become.
Yeah, sure.
What other comments that, you go to a talk and you'll start with Z2 cross Z2. The first question you ask, why not just one single Z2? Why two? Well, the reason is because you just have one Z2, there's no non-trivial SPT. So this is the simplest non-trivial. Not making your lives more complicated. Okay, good. Now, let me just say quickly that in the continuum, let me give some continuum information. You can choose the product state to correspond to a trivial partition function. The Z here stands for the partition function of your continuum theory. And you can take the product state to correspond to in the low energy, some trivial partition function where the partition function is always one. And for the cluster state, you can take it to be e to the I a even where A even A odd are the background Z2 gauge fields or Z2 odd. And since these are background gauge fields, the difference is just a constant. It's something really trivial that we usually model by. Great. Now I'm still not yet at the non-invertible symmetry, so let me continue discussing how to distinguish these two phases. So there are many ways to distinguish different SPT phases. Now let me present the first one. The first one is to look at the string holder parameter. So as I said, if you just look at the spectrum, you're not going to see any difference between the two. Well, let's take a step back. So usually if you have a symmetry breaking phase versus a symmetry preserving phase, how do you see the difference? You can look at the spectrum, that's fine. But you can also look at the older parameter. And the older parameter will have different asymptotic behavior at large distances. Now for SPTs, if you just look at the older parameter for local operators, you're not going to see the difference. They're both trivial. But if you look at some string order parameter, I'm not going to get into the details because there's a better way to say this. The better way to say this, I think is first recognized by Kennedy and Asaki, is that you can do a transformation known as the PD transformation, Kennedy and Asaki, to map these two Hamiltonians to two different Hamiltonians. And the two new Hamiltonians, which are called H hat, trivial, and H hat cluster. These two hatted Hamiltonians will have different symmetry breaking. So by KT, you can map the more subtle SPT phases to more subtle SPT phases to two very conventional Landau paradigm symmetry breaking patterns. Now, this is the condensed matter physicist's way of saying it. From the continuum point of view, what we are doing here is gauging. By gauging the two V2s. But more precisely, we're doing a twisted gauge. We're doing the so-called TST. Now, if these words don't make any sense to you, that's fine. SNT stands for elements of the modular. But it's just some twisted gauge. The fact that it's twisted doesn't really matter. It's more of a cosmetic choice. But now let me say a little bit more about this gauge. So I'm not going to do the details, but you really do the usual thing that you do when you gauge a symmetry apparatus. You introduce gauge fields on the links, and then you impose Gauss law. You remove the original degrees of freedom by solving the Gauss law condition and rewrite the Hamiltonians in terms of the new degrees of freedom. And at the end of the day, this KT transformation implements the following transformation. You can think about it as a gauging method. So I distinguish the new variables from the old ones by the hat. They're really not the same. These guys come from the gauge fields you introduce to gauging.
So I know how to think about twisted gauging and continuum, but how should I think about it on the lattice?
Yeah. So S is just the ordinary gauging. The T just means that you perform a unitary transformation on the output. In fact, that unitary transformation is exactly the same thing. But that's really just a technical point. Yeah. So I could have stated the whole story without the T here. I can just do S. It's just for historic reason and cosmetic reason. It's better.
Yeah, so does this always work? That if you have some different SPT, then you detect different gauge?
I think it always works. I don't have a complete proof. I think it should be, yeah. Let me not make any general statement, but I think it always works. For my purpose, I only have to talk about it. Yeah.
Doctor state also has a time reversal. So it can also be composed of then it's protected by the time reversal.
Right.
What happens to that? You know?
I think time reversal is probably, I don't know. Probably it's different. I don't know. I never thought about it. Yeah.
You only require a single Z2 time reversal to protect the phase, right? Just one Z2 time reversal center.
1 plus 1 is that right? Oh.
Yeah, I think that's 1 plus 1 is the time reversal.
Pick W1 square.
Oh,
Let me
W1 square, I'm sorry.
Stable when you
Yeah.
have W1 square.
But I think doctor state is like, I mean, in fact, the
Sure.
state is like,
Yeah, there should be something interesting about time reversal. But anyways, I'm putting that aside.
So just double check. So the T there is similar transformation as V.
Yes.
So and V square is 1. So you are doing some kind of a V as V inverse, that type of thing.
Sure.
Right. To
Pretty much everything's over there too. So if you do this KT transformation, the trivial becomes, yeah, the trivial is still trivial. The cluster becomes -1. Okay. Now, if you stare at these two Hamiltonians, they're definitely different. This has a unique ground state because it's the same as the previous one. But this one has 4 states on the closed chain because you have all the z hat correlation among the even side and among the odd side. So this corresponds to the phase where Z2 even, Z2 odd is completely broken. And this corresponds to Z2 even, Z2 odd phase that are completely unbroken. So this is a nice way to distinguish the two SPT phases. The idea is that you do a gauging from a continuum point of view, or you do a Kennedy-Kawasaki transformation from a matter physics point of view. And that this transformation will map the 2 very subtle SPT phases to 2 very different phases distinguished by the ordinary Landau theorem. Okay. And this will be the trick that we will later on use to distinguish different non-vertical SPTs. So that's the first diagnostic of SPTs. And after the KT transformation, we see that these are 2 different Landau phases, and therefore, before gauging, this has to be 2 different. Okay. Now there's a second diagnostic which was already mentioned in the questions, is to look at the attribute.
Actually, just make sure, sorry for that.
Mhm.
So the
Yeah.
first part, so you are mapping the two relative SPT phase to two different symmetry breaking phase.
That's right.
So how do I think this from maybe more field theory point of view?
Good, thank you. I should have mentioned that. Let's do it here. So this is, so by doing T, what you do is to stack this counter term. This counter term is invariant under S. So let's do it carefully. So you start with 1, you do T, you get the better notation. Well, okay, I'll just write it. This is T, and the S leave it invariant, and then you stack another T, it goes back to 1. So this is the sequence that takes you from this to this. Alternatively, you can start from cluster. When you do T, you trivialize the original counter terms. And then you do S, you go to a symmetry breaking phase. And then you go to T, you are still in the symmetry. And that symmetry breaking phase is this. This is the continuum counterpart of the Kennedy-Cassandra transformation.
How do I understand doing S will lead to symmetry breaking phase?
So the gauging always exchanges the trivial phase to the gauging always exchange the untwisted gauging always exchange the older and the disorder. You can think about it in terms of the
Thanks.
okay, good. So now let's move on to the attribute. So what do people usually say about clusters? They say, you put a cluster on an open chain, then you see the boundary degeneracy. But then there's a question about what do you take to be your symmetry operator, especially around the edge. And personally, I think that discussion might lead to many confusion because you need to cut open the symmetry operator. And the moment you cut open the symmetry operators, there will be options. Alternatively, let me present a different presentation where you never have to cut open the symmetry, but you have to change your hump. So instead of putting a cluster on an open chain, I'm going to think that I have a closed chain. It's just that on one half of the closed chain, I have the product state. So let me be more precise. So this is my chain. This is site number 1. This is site L. But somewhere in the middle, let's call it L prime. L prime can be L over 2. It doesn't matter. Just somewhere in between. In this region, I put a cluster. And in this region, I put the trivial. And the detailed Hamiltonian looks like this. So I'm going to call this Hamiltonian the interface. It's really not that different from the things that people usually do. So what people usually say is that put it on an interval. My interval has L prime sites, and this is my open chain. I'm just making a very, very minor modification that I'm thinking about it on a closed chain, where on the other half of the closed chain, I have a trivial. Okay. Now, the advantage of doing it this way is that I never have to cut open my symmetry operator. This is eta even and eta odd are still symmetry of this interface. Okay. But now the interesting thing about this interface Hamiltonian is that here I have L minus L prime terms. Here I have L prime minus 2 terms. It's easiest to look at the position of the X term to see how many terms we are missing. Still, there are commuting stabilizers, and I have 2 less terms compared to these 2 guys. So I have 2 less constraints, and that leads to a 4-fold difference. It's basically the same thing that people usually say. But the reason I want to do it this way is because in the usual discussion of SPTs, the product state is always one of the SPTs. In fact, that's how people define to be a trivial SPT. But in the story of the non-invertible SPT, at least for the one I'm going to talk about, the product state is unfortunately not an SPT. So I actually cannot cut it open. I have to consider interfaces between two different non-invertible SPTs. So to prepare for that, I'm setting up the cluster discussion in a similar manner. But as it's clear from the presentation, it's really not so different from the ordinary, right? Because you just take the coefficient of this guy to be very large, you ping down the qubits on half of the chance, and it's as if you are on the whole chain. But the advantage that now I can always work with the symmetry operator.
So, excuse me.
Yeah.
So is that statement is general true that the trivial product state, which looks something more like a partition function as one, is not invariant on the non-invertible symmetry?
It's not a generally true
It's
statement.
not general.
Yeah, it depends on the presentation. In fact, I can do a unitary transformation of my non-invertible system so that the product state is an SPT. It's just, so that's another thing I want to emphasize. There's really nothing secret about the product state. It's really just a choice of the reference point. It's just in my presentation, as you will see, it's not natural to take the product state as an SPT. But it's not the invariant statement. And the most invariant thing is always to think about interface. It's only the difference between SPTs that matter.
Yeah, how important is it that these are technically subsystems?
Wait, sorry.
Like, one's only acting at even sites, one's only acting at odd sites.
I don't think it matters that much. I think you can even group the two cells into one cell. Group the even and odd into one cell. I don't think it matters that much.
So just again, come back to the point that whether the product state can preserve non-invertible symmetry, this statement. So if I just think from the maybe more partition functional field theory point of view, so how do I see the possibility the product state may not preserve non-invertible symmetry?
No, you cannot see that because there's really nothing sacred about the product state. Here we just make a declaration that the product state corresponds to the trivial partition function.
Right.
But you can make a different choice.
Okay.
There's really nothing sacred about it. Yeah.
I see. But if partition function is one, it's just in the field theory, there's an expression. Can you see non-invertible symmetry X on this in the non-invariant way? Suppose you maybe write in this portfolio.
So I actually don't know how to write well, when we get to the non-invertible case, we don't have the background gauge fields for the symmetry. So that part of that story is not there.
Okay.
You have to take the Poincaré dual for it to make sense.
So you don't know the analogy.
I don't know the analogy of this discussion, but you can take the Poincaré dual, then I know the analogy. In fact, it's not that I know the analogy, it's that the mathematician worked it out 24 years ago. So the purpose of this talk is to reproduce mathematicians' classification of lines.
Okay.
Yeah.
What's the symmetry of your interface system?
Good, I'm getting into that. So these two are obviously symmetries of the interface system. Okay, as you can check. Now the question is, what are the other symmetries? I can give the answer, but let me present it in a slightly different way. So take any one of the ground states. So there's a four-dimensional ground space. Take any one of them. What you can do is to compute the action of the symmetry operator on the ground space. Now, eta even is the product of x even. Now, the thing that people usually do is then to write x even using the stabilizers in terms of the z's. Okay. So let me spare you the details, but the idea is that deep in the bulk, if you have a product of x, you can replace it by the product of zz, but then the pair annihilates. So this global symmetry operator localizes to the two edges. And what you end up finding is that it equals Z1 equals, let me write it more illuminate more. What you find is that this global symmetry operator is factorized into two local factors. This guy is E1, this guy is E alpha minus 1 times alpha. Now, the interesting feature of these two terms is that now if you consider eta odd, eta odd commutes with eta even, but it anti-commutes with this equal factor. And that's the reason why we have this fourfold degenerate, because of this local projective algebra. Globally, there's no projective algebra because the two minus signs cancel with each other. And back to your question, this guy is actually also a symmetry of the Hamiltonian. It's a local term, but it comes with this. The only reason we didn't add it to the Hamiltonian is because it doesn't respect that it's not Z2 plus Z2 symmetry. The anti-commutes with it. This is true for left and also for right. All right, so these are two different ways to detect different SPTs. One is by gauging, the other is to set up an interface and see if the symmetry operator factorizes and if there's a projective algebra realized locally. And now, having set up the stage, I'm going to move on to the non-invertible. 5 minutes. All right.
Actually, before that, sorry.
Yeah.
Could you maybe briefly comment again what you could do to change boundary conditions to make these technologies go away?
Oh, yeah, I could. That should really be a separate discussion, but since this is more of an informal talk, just do it in real time. So in that case, I'm really on open. Now instead of taking this Hamiltonian, I can take this. I'm just going to write the which one? Sorry, let me do it differently. Then the last one. So the idea is that instead of writing ZXZ on the boundary, change it to XZ. So this Hamiltonian on the open chain, locally, deep in the bulk, looks identical to the cluster Hamiltonian. So it qualifies as an open chain version of the cluster Hamiltonian. It didn't touch the bulk. But this Hamiltonian has this one. Ah, I missed one. I'm sorry. This term is still CL1 minus 2. And then the last term is this. So I have L prime terms. They all commute with each other. So I have a unique ground state. So this is an open chain cluster Hamiltonian with a unique ground states on the interval. Now the question you will ask is what are the symmetries? I must have messed up the symmetries in some sense. Well, let's take a look. So eta even deep in the bulk, it has to be x2, x4, something. But here to fix this term, I'm going to add this one. And all the way to here, let me assume L prime is even. I think I just go all the way to XL prime. I don't do it. I think this works. And eta odd is x1, x3, all the way to XL prime minus 1, and then you take the two Z2 operators locally again, is the product of X. Now you might complain that globally there's a Z on the boundary. But you introduce a boundary, you are supposed to make some modification at the boundary anyways. And another way to justify it is that when you take the original symmetry operator, you can view it as a product of X. You can also view it as a product of ZXZ. And if you view it as a product of ZXZ, you naturally get this Z. And this completely aligns with continuum intuition. The cluster state is a trivially gap-based where the Z2 cross Z2 does not have an anomaly. If it does not have an anomaly, there better be a boundary condition preserving the symmetry with no degeneracy. This is it. But people don't like to talk about it just because of that Z. But it's really about, so there's nothing wrong with the way people usually talk about it. People demand a strict on-site symmetry. They don't even want the spreads between three sides. They literally want the symmetry to be product of X, even on an open chain. If you make that strong of a requirement, then you are forced to have degeneracy. But I think a better way to say that is that you work on an interface and you never cut open the symmetry. All right. So finally, we can talk about non-invertible symmetry. So the almost trivial observation that we want to make is that take the cluster Hamiltonian. Is invariant under this transformation. That you can see with naked eyes. This is just a transformation exchanging this pair with this term in the middle. Okay. Now, is this an ordinary symmetry? Well, there's a very simple argument telling you that this cannot be implemented by an invertible operator. If there were such a, I think many of you have heard this argument, so I'll be quick. If there were such a unitary operator, such that UXJ, U inverse is UJ minus 1, UJ plus 1, then just consider U, say, A not even, U inverse becomes 1. Because you replace each X even by ZZ, but then ZZ pair annihilates. You get 1, and that's a conjunction. So this transformation cannot possibly be implemented by an invertible operator, and it has to be implemented by non-invertible operator D, and the precise meaning of this arrow is DXJ, J minus 1. Sorry, I was going a little bit fast because I think this is the 5th time I made this argument. Okay. So there is such an operator D. In fact, you can even write it out very explicitly. If you have heard my talks on the Ising model, this D will be closely related to the D in the Ising. It's roughly speaking the product of the Kramers-Wanier operator for the Ising model on the even side and on the odd side. But on top of that, you also have to do a lattice translation. That's what makes more interesting. So let me not bother you with the details of the explicit expression for this operator. It's something you can write in terms of the topologies. The important thing is that when you compute E squared equals 1 plus eta even plus eta r plus eta even thing. We emphasize here that P inverse does not exist. So this is already different from the Ising case. In the Ising case, D squared involves the lattice translation. But here, for the cluster, it doesn't mix with the lattice translation. It's an internal non-invertible symmetry. And you also have algebra that D, eta, even or odd. So in total, this is the fusion ring for one of the fusion categories that might be familiar to some of you. It's called the Z2 even times Z2 times Z2 Tambara Yamakami. Now, for those of you who have thought about the Tambara Yamakami fusion category, you will know that in this particular case for Z2 cross Z2, there isn't a unique Z2 cross Z2. There are actually 4. They are distinguished by characters and convenience sure indicator. Those are details that you don't have to worry about. And what we are able to do in this project is that we identify which one of the 4 fusion category does this D belong to. And the answer is that it actually forms a RAP D8. There are many different ways to argue this. You can even do the explicit F symbols on the lattice, or you can do the gauging argument. But let me not get into that. Now, let me just say that what RAP D8 means. D8 is the dihedral group of order 8. RAP means that you are looking at the fusion rings of the irreducible representation, like group of order 8. Now, the dihedral group has a 2-dimensional representation, and that's associated. You can recognize that this is actually a representation ring. Okay, so what we are saying is that if you take the clusters, you can add with eta even or odd, still give you clusters. It's a trivial gap phase with eta even and eta odd. But what we are adding to the story is that it's also invariant under D. Here for non-invertible symmetry, invariant means that you have to put Q. It's like the function dimension. So the upshot is that the cluster is not only a Z2 cross Z2 SPT, but it's actually a RAP D8 SPT. However, the trivial phase is not the RAP D8 phase, because you can see that the trivial Hamiltonian is not invariant under this, but the cluster is. And that's the reason why the product state, our presentation, is not a RAP D8 phase. So this is the easy part. Now the difficult part is I'm saying that the cluster state is a non-invertible SPT. I should say that by non-invertible SPT, I just meant that it is a trivially gap phase that's invariant under a non-symmetry. But the immediate question that people will ask me is it a non-trivial RAP D8 SPT? Now my first answer is that that's not a well-defined question. So SPT, you can never pick a particular SPT and ask me if that's trivial or not. Just like in the product state versus the cluster case, there's really no sense that the cluster state is more non-trivial than the product state. And here, so far, I only presented you one such SPT, and it is what it is. You cannot say it's trivial or not. In fact, the product state in this case is not even invariant under the non-invertible symmetry. So you don't even have that natural reference. However, the more interesting question is the following. Mathematicians, more precisely Kambara, in year 2000, classify mathematically what are the representations of the RAP D8 fusion category. Well, he did it more generally. He did it for both Kambara and Madame. And it is known that Kambara find out that there are actually 3 one-dimensional representation of one-dimensional module category size for the RAP D8 fusion category. So in this language, it means that there are 3 distinct RAP.
Yeah, sorry, there's 2 questions. So first, is that what the same thing as what we say fiber functor?
Yes. So there are 3 fiber functors of the RAP D8.
And is there a notion of stack?
No, there is no notion of stacking. So that's another interesting thing, that for invertible SPT, even though there's no natural notion of a trivial SPT, the difference between that form, right? But not for non-invertible SPT. There's no group structure. And there's a consequence of that statement on the lattice, which I may or may not. So the mathematicians told us that there are 3 RAP D8 SPTs. And here we said that cluster is one of the 3. where are the other two? And if we can find the other two, we can then study their differences. Their differences don't form a group, but you can analyze the edge modes and identify and really see that there are two differences. So in the rest of the talk, I will tell you a very easy way to construct the other two SPTs. And you will follow the same strategy I outlined. Okay, is it clear so far?
Maybe you'll say it, but just make sure. So what's the statement that Imara's paper make?
There are three
Three
fiber
fiber
bunkers
bunkers.
or one-dimensional module categories of the RAP-D8. By the way, one way to, sorry, just one comment. One way to see the three is the following. Z2 cross Z2 as a group has three non-trivial elements. There's an identity, but the other three are older two non-trivial elements. And these three RAP-D8 SPTs are permuted by this triality of. If you look at Z2 cross Z2, you cannot look at any one of the three non-trivial elements and say that guy is more non-trivial than the other two. The threes are really on the same footing. And that's the reason why among the three RAP-D8 SPTs, they're really on the same footing. You cannot say one is more trivial than. Yeah.
I'm not familiar with noninvertible SPT, but we care about the two-dimensional ERAP of.
Yeah, we do. I mean, that's associated with this non-invertible algorithm. It's okay that you know. I think this is a very. This is not a subject that every physicist is familiar with, but hopefully the point of this talk is that we can put it into a very concrete lattice setup, where I can, at the end of the day, I can write down a state that represents this mathematical SPT.
So they don't have the bolts don't have a sense of stacking.
There's no stacking.
Do the edge modes have a sense of stacking your group, or also not as well?
I don't know what that.
I'm trying to think if there's some. I guess you can never fuse them without getting to the one in the middle. So you like put lots of domains.
Yeah, I don't know how to. I don't know how to stack.
Okay.
The reason is because there's no such a thing as a diagonal category. There's a diagonal subgroup, but not a diagonal subcategory. All right, so to find these two other SPTs, we can actually follow the same strategy by doing the Kennedy-Tasaki. So the idea is that here we have the RAP-D8 SPT. And cluster is one of them. And for the other two, let me call them even. The reason is because, as I said, the three are distinguished by the three non-trivial elements of Z2 cross Z2. The three non-trivial elements are even, odd, and diagonal. You can view the cluster as diagonal. So that's the reason I call the other two even and odd. Now, if you do a KT transformation, we have already talked about the cluster case. The cluster case will correspond to the Z2 cross Z2 broken. Okay, I should have said another thing. Here we have three distinct RAP-D8 SPTs, but they are really the same Z2 cross Z2. So if you forget, so just like if you forget about the Z2 cross Z2, the cluster and the product are the same. They only bifurcate when you impose the Z2 cross Z2. These three SPTs, they are the same Z2 cross Z2 SPT if you forget about the non-invertible symmetry D. They only become different when you impose the non-invertible symmetry. And that tells you that these three non-invertible SPTs under the KT transformation should all be mapped to some Z2 cross Z2 broken bits. But now we have one more symmetry. Then on this side, we have E, we have eta even, we have eta odd. Under the KT transformation, we basically do a twisted gauging on even and odd. So that will lead to some quantum symmetry data even at odd. And that's the Z2 cross Z2 that will be spontaneously broken in all three phases. But we also have to track what happened to D. But it's a one-line computation to show you that this D actually becomes an invertible operator D hat, which is a product of the CV gate. So on the one hand, before KT, you have a RAP D8S. After KT, what you have is a Z2 times Z2 times Z2 symmetry breaking phase. Well, these three phases, Z2 even and Z2 odd, are all broken. So the question is, what is the unbroken subgroup inside this Z2 cube? It's very easy to see that the cluster preserves Z2B. I'm skipping some details, so you probably have to take my words for it. But let me just continue. I can show you the calculation if you're interested. Let me just be clear.
You can take your time if you want.
But everyone will get hungry. I will also get. So the cluster preserves the unbroken subgroup in Z2B. So you might say, okay, maybe that's it, right? You necessarily have to break this two. So the preserving one has to be this one. Well, that's not quite it. Because if you think about symmetry breaking, the unbroken part is a subgroup. The broken part is a quotient. So without specifying the subgroup, you don't really know your symmetry breaking. More specifically, you have another option where the unbroken subgroup is Z2V times Z2 odd. And there's another option where unbroken subgroup is Z2V and even. And I claim these are the three non-invertible SPTs. So the statement is that the non-invertible SPTs after Kennedy, so just recall the cluster and product case. After the Kennedy-Tasaki transformation, the two SPTs become two different symmetry breaking patterns for ordinary invertible symmetry. Here we have three RAP-D8 SPTs. After the Kennedy-Tasaki transformation, they become something really standard. These are just three different symmetry breaking patterns of the Z2 cross Z2 cross Z2 symmetry. A priori, Z2 cross Z2 cross Z2 symmetry can have more symmetry breaking patterns. But since we know they are all in the same Z2 cross Z2 SPT, we know this part has to be broken. So it's like you fix the quotient part of the symmetry breaking pattern and you try to determine the subgroup. That's all. Now, for those of you who are paying attention at this point, you should ask, shouldn't there be a fourth option? Namely, what if it's the diagonal of the three that is unbroken? Let me write it here. But Tambara told us that there are only three such SPTs, so there better not be a fourth one. Now, in fact, this fourth one cannot be realized. And this is because, what's the symmetry here? This symmetry is
because there's some anomaly.
yes. This symmetry is the famous symmetry in the CZX model, which is known to have a Levin-Gu H3 type anomaly. And since it has an anomaly, it cannot be the unbroken sum. So in fact, this three symmetry has a type 3 anomaly. It's an A cup, AB cup, A even cup, A odd anomaly. And the type 3 anomaly forbids this symmetry breaking scenario. Okay. Great. So now we have provided a very simple understanding of these three non-trivial, three RAP-D8 SPTs. And from this algorithm, you can easily figure out, come up with an example of the Hamiltonians on this side that represent this symmetry breaking path. Right, on this side, we're just dealing with invertible symmetry. There's no funny business. You just have to come up with some Hamiltonians represent this symmetry breaking path. Let me not bother you with the details. So we did that. And the moment you find the Hamiltonian on this side, you can easily take it back and find a Hamiltonian for this other two RAP-DA SPTs. Let me tell you the answer. So I'm just going to do it for the odd state. The even state works in exactly the same way. You just have to do a lot of translation. So for the odd state, well, let me write down the state. Odd state is a stabilizer state. And the stabilizer codes are the following. Make sure. So recall the cluster state is a stabilizer code where all the ZXZs are +1. Now this odd state is a little bit different. First of all, L has to be 0 mod for here. Don't worry about this. I think when L is not 0 mod 4, it corresponds to a certain sum. Now for the odd state, half of the stabilizers are still ZXZ, except that there's a minus sign. And the other half become YXY. Anyways, this is what it is. Try to follow this algorithm. And you can write down Hamiltonian for this stabilizer code. Well, you might say that I already present you the stabilizer code. So writing down the stabilizer Hamiltonian is totally trivial. Just add these terms to them. It's not that trivial because this term is invariant under the non-invertible symmetry, but not this term. So you actually have to correct the stabilizer. But you can do that, and let me write the answer. These two terms are the stabilizer terms. This term is a correction term to make this combination invariant under the non-invertible symmetry. Right, okay, so this is the final answer, that this is the stabilizer code for SPTs. Now let me make a comment here. You can write this state very explicitly. In fact, you can write this odd state following brackets. By the mouth. Let me just tell you the qualitative features of this one. So the cluster state is a very concrete state. The odd state can be obtained by applying this finite depth local unitary. This finite depth local unitary, each individual gate is C2 cross C2 there, right? Because this guy, these two guys are odd. On the odd side, these two guys are on the even side. And here I always pair up the even with the even, the odd with the odd, the odd with the odd. So the local gates are Z2 cross Z2 symmetry. It's a finite depth local unitary. That means if you forget about the non-invertible symmetry, this is really the same Z2 cross Z2 SPT as the cluster state. However, the gate is not impacted. Then the entire unitary is not invariant. Okay. All right. Think actually, let me just make another comment. So I don't know how many of you are familiar with the ZX calculus. That's something that the quantum information theory is like this. So this state has a very nice presentation in terms of the ZX calculus. So the cluster state in the ZX calculus take this form. Where the box is the hegemon. The circle is some states that some tensor like this. Anyways, if you never think it, that's fine. But I just want to draw it.
So what's the circle again?
It's some tensor.
Can you write it?
I just did.
I didn't pay attention, but it really erased.
Now, what is the R? First, you put the pi here. Then you first have to change it to a pi naught. And you connect it. You have to make a decision that whether you start with an even side or odd side. That's what breaks the lattice translations. Anyways, this is also one presentation for this. Okay, so in the remaining 10 minutes, let me talk about the edge. Since the product state is not a replicated SPTs, I really have to consider interfaces. So let me prepare interfaces. Okay. One. Now. And here I put the Hamiltonian for each arm. And here I put the Hamiltonian plus E. And at the interface, I have to do something. Yeah, let me not bother you with all the technical details. But again, just like in the cluster and the product state interface case, you'll see you can just count the number of turns in the Hamiltonian. They're all commuting projectors. And you find that the ground states. So there's a local degeneracy on the two ends. Now, if you remember in the cluster and the product case, the eta factorizes to two local factors. The local factors obeys a projective algebra. What's the counterpart here? First of all, there's not going to be any projective algebra among the Z2 cross Z2. Because these two states, they are in the same Z2 cross Z2 SPT. The projective algebra only occurs when you include the D's. So what we should do is to look at how the non-invertible symmetry acting on the state on this ground space. And this is a very interesting calculation. I mean, this calculation took us a month to figure out how to do it. Actually, at some point, I tried to use the ZX calculus. I think there's a way to do that, but I guess I'm not very good at this ZX calculus. You have to use some Hopf algebra to simplify the diagrams. But at the end of the day, what turns out to work is to take the explicit expression of the operator D in terms of the sequential quantum circuit. And then you can use that expression and do a lot of simplification. It's not a trivial algebra. We spend a lot of time figuring out how to do it. The final result is the following. But recall that in the cluster case, what we have is eta even acting on the ground space. It becomes eta even left, eta even right, and but for non-invertible symmetry, you don't just get one factor. You actually get a sum of two factors, each of which factorize into the local operators on the left and the local operator on the right. Well, I can give you the explicit expression. It's not terribly illuminating. Like this guy is E1, this guy is something like minus I Z L prime 1, Y L prime 2, X L prime 1, prime. It's not terribly. But the upshot is that D does factorizes into local factors. But there's an important thing that it's a sum of two terms. So that's something fundamentally different from the invertibles. Now, where's the projective algebra? Well, the projective algebra happens by looking at this guy, for instance. It has a Z1. And Z1 is odd under the eta symmetry. So eta odd anti-commute is, it works for 1 and 2. I think it also works for the byte factor. So these 4 local factors, the anti-commute eta odd. Now eta even actually commutes. We break the symmetry between even and odd because here I'm looking at the odd state. So this is the projected local projective algebra for the non-invertible space. Okay, that's all I want to say.
Thanks very much. Question, comments?
Maybe like super. But like you said something about the product state being like a choice. That's correct. But like, or you also said like the edge modes are choice like boundary condition. Like if I think about this, so like that does have edge modes.
Yeah.
Another makes sense.
Well, there's nothing wrong with that, right? Just like for the cluster, you can. The point is that you can view the other side of the boundary as a product state.
So I should really be thinking of the interface.
Yeah. It's just a slight change of perspective. That boundary is not the end of the world. It's an interface to a trivial place.
I mean, not all complex ones later is like the vacuum is a super well defined. A lot of them, it's like you have to decide which C2. Yeah. So only domain will.
Like when you do the calculation, it's like M less than 0 side, M greater than 0 side.
Yeah.
Like you by hand choose like
Exactly.
what side like the F wedge F term actually.
Yeah, it's basically the same. It's related to the biofermion example.
Sorry, the ground state of that was this interface to the interface is full. So which will be similar to the case of the 1 + 1 dt to the dt to SPT.
Yes,
It's
it's just that
right?
here you have a sum of local factors. That's one difference.
you ever consider the defects related to this symmetry?
Absolutely, yeah. So we are writing a short paper just about the operator and the basis. We have a longer paper about the defects. In fact, you can, so you can talk about the defects, and you can reproduce the entire module category on the lattice. All the F move, all the F tilde symbols, it's all there on the lattice. In fact, we first computed all the F and F tilde symbols on the lattice, and we identified which phase is which. And it's only later on that we figure out this simpler argument.
So, because I always have the impression that the non-verbal symmetry is related to some like keep of certain lattice size. So with the theory, we also have this kind of thing. That we lattice or
So the defect for this non-vertical symmetry D requires you to add an extra qubit. That's reflected in the fact that it has only dimension 2.
So between these three SPT, is it like a affine space? Like, does it have any structure? So it just
I
have
don't think it has any structure, not that I know
And then how general is kind of this method of going to kind of like this dual?
of. I think it's general. I think it probably works for strategy.
But you kind of banking on the fact that on the other side, you kind of have this, I guess, like a
Right,
description,
right.
no.
Yeah. Well, it does have a nom.
Right, yes. But does all same fusion category has
It's definitely not all fusion categories, but I would guess Rep G always be. I'm not sure. Yeah, let me not make a general statement.
Okay.
Yeah.
one question I have is, so this is all in 1 + 1D. So in 2 + 1D, I want to imagine something similar to that equation happens, where it's like a sum of 1D phases. Do
Interesting.
you have any thought about how the edge modes in higher dimensions generally?
I haven't thought about it, but we do have a model in 2 + 1. Because the cluster Hamiltonian is generalized
Yeah.
to higher.
It doesn't have to make 0.
That's right.
They're analogous. We can also start from 1 + 1D Zn times Zn SPT.
Yes.
So there should be some transition 2 to general integral.
Yes.
Do you know the structure?
I
Maybe.
think it will work almost.
Yeah,
identical. There's no interest in dependence on it.
That's the paper you refer to this.
We only work.
Tempara has worked out this.
Yeah.
Zn times Zn. Sim-
Yeah.
Tempora.
Sorry, you're right. That the
Tempara.
classification of the SPTs. No, I shouldn't say there's no interest in dependence. There will be some interest.
So I said with the Tempara has worked out
Yes,
the analogous thing.
Yes.
He worked out more
It
than
did.
2 times it, but
It
he
did,
did.
it did. I think it worked it out for general Abelian groups. That's a good point. Yeah, maybe for Zn cross Zn is complicated. But you can see where that happens, right? Because then you will have probably Zn cross Zn, and then there are just more symmetry breaking. It's equal to breaks.
Okay. All right, thanks. Thanks, Shu-Heng.
All right.
Thank you.
I'm wondering if you'll still be around this Saturday.
No, I'm leaving tomorrow.
About the investors, Chinese summit.
Oh, I
Maybe next, yeah, we have